I am extremely happy to meet the viewers of my YouTube channel in yet another video, state space analysis using phase variables. I have presented this concept, state space analysis using phase variables, in two parts. The first part I am going to deliver now. Let me move on to the presentation straight away. The learning objective of this presentation is to obtain the state space representation using phase variables from the mathematical model. In the last few videos, we have seen how to obtain the state space analysis using physical variables, that is by considering the actual physical system involving the components of the system. How to obtain the state model we have seen. So let me recall how I have done. So we have assumed the state variables pertaining to the variables involved in the energy storing elements of the system. So we know very well that we have taken as many state variables as the number of energy storing elements in the system. That means the actual physical system involved or the actual physical system under consideration is used for selecting the state variables. Suppose we don't have the system before us. Rather, the mathematical model of a system is straight away given to us in the form of transfer function or the differential equation, how to do it. So one of the methods to do this is applying the state variables from the mathematical model and then deduce the state space analysis. So let us see how it is done. So here we are going to take what are called state variables using the phase variables. So one of the system variables is going to be taken as one state variable and the derivatives will be taken as other state variables. For example, if we have output of the system, output is taken as one state variable. The remaining state variables are derivatives of output. That means if output is y, x1 is y, x2 is y dot, x3 is y double dot, x4 is y triple dot, and so on. Like that it is done. And the state model using phase variables, you can easily determine if it is already in the transfer function or differential equation form. So we will see that it is going to be solved by using a form called Bush form or companion form. So let us understand this with the help of an example. So consider a nth order differential equation relating the output with the input of the system. So here yn is nothing but nth order derivative or nth derivative of output. This is n minus 1th derivative of output, n minus 2th derivative of output, second derivative of output, first derivative of output, output itself. The right hand side contains only input, no derivatives. That means if you take the Laplace transformation, right hand side will be deciding the zeros. There won't be any zeros because there won't be s term in the right hand side. Therefore, this is going to be the state space model using phase variables for transfer function without zeros. That is, we are going to see how to do it for a transfer function without zeros. So as we have already indicated, output is taken as one of the state variables. So output is taken as one of the state variable and remaining state variables are derivatives of output. So y is the only output. So x1, derivative of y is what? X2, second derivative of y is x3, so on. Finally, nth order derivative of y is xn dot, right? So because y double dot means x3, y dot means x2, therefore yn minus 1 means xn, because double dot means here 2, here 3. So n minus 1 means n, therefore yn is xn dot. There is no xn plus 1 because there are only n state variables. So now we are going to make use of these equations or expressions and substitute the same in the differential equation or mathematical model of the system to rewrite the same using state variables. For example, yn. What is yn? xn dot, that's all, plus a1. What is yn minus 1? xn, a1, xn. a2 yn minus 2, that is y2 xn minus 1, plus etc. an minus 2 y double dot x3 plus an minus 1 y dot. What is y dot? x2 plus an y. What is y? x1 equal to b into u. So if you rearrange this properly in such a way that all the state variables are written in the right hand side along with the input, only the derivative of the state is in the left hand side, then xn dot is minus an x1 minus an minus 1 x2 minus an minus 3 x3 an minus 2 x3 etc minus etc minus a2 xn minus 1 minus a1 xn plus bu. So this is going to be the state equation corresponding to the nth derivative. Actually we have to write n state equations because we know very well that if the order of the system is n, we have to have n state variables. So n state variables and n state equations. And developing the state equations is nothing but decomposing a nth order differential equations into n first order differential equations. This concept we already know. So we have written one state equation. Rest of the equations are very simple because y is x1, y dot is x2. What is y dot? x1 dot, x1 dot is x2. Y double dot is x3. What is y double dot? Y double dot is x2 dot, etc. So here yn minus 1 is xn, means xn minus 1 dot is xn. That is xn minus 1 dot will be the previous one corresponding to yn minus 2. 1, 2. That when you differentiate, you will get yn minus 1, yn minus 2 on differentiation. Therefore, xn dot on xn minus 1 dot on differentiation is xn. That's all. So there are n state equations. These n state equations are written in the form of vector matrix notation. We know how to write the vector matrix notation. So derivatives of state, that means this derivative of state vector is in the left hand side. The right hand side we have state vector and the input. So we have to write it in the form x dot equal to ax plus bu. So here n derivatives of state are there. So here x1 dot is x2, means the first derivative of state vector is related to x2 alone. So 0, 1, rest of the element 0. x2 dot is x3. So 0, 0, 1. Third element only x3. So rest of the element 0. Likewise xn minus 1 dot is 0, 0, etc. xn minus 1 dot is x1. So here we have to have n minus 1 dot is x1. So we have to have 1. So let me write 1 here. So here we have to have 1. That is this one corresponding to xn minus 1 dot, we will have 1. Right? So if we see all these elements, corresponding to xn dot minus an minus 1 minus an minus 2 minus an minus 3 etc minus a1. Then corresponding to u it is b. There is no influence of u with respect to other state equations, no u term, so 0, 0, 0. So if you carefully go through all this, so what we can understand is the elements just above the main diagonal, this is the main diagonal, the elements just above the main diagonal, they are 1, 1, 1, 1, 1. The last row, if you see, coefficient of x1 is minus an, x2 is minus an minus etc. That means we are writing like this. This minus an is nothing but coefficient of y with negative sign. an minus 1 is coefficient of y dot with negative sign. That means we have written this a1, a2, etc. an in the reverse order with a negative sign. So that is why I said system matrix A is in a special form called Bush or companion form. So it has unity elements just above the main diagonal. Last row has got negative of the coefficients of the original differential equation, but written in the reverse order, not minus a1, minus a2, etc., but written in the reverse order. Rest of the elements are all zeros. So this is the standard form of the state equations. Considering the matrix B, we know all the elements except the last row are 0. So except the last row, all the other elements are 0. Right. Now if you see the output, we have taken x1 as the output because that is the first assignment for the state variable that we have considered. Therefore, y is 1, 0, 0, x1, x2, etc. xn. So y is equal to cx. Therefore, that C matrix or that C vector is a row vector is having 1 as the first element. Rest of the elements are 0. So this is the output equation. So this is how we have to write the state space model if we are given the mathematical model in transfer function form or differential form without zeros. Let us see with the help of an example. So construct a state model of the system characterized by the differential equation. This is a differential equation. So this is actually in the same form of this. It is in the same form as this. Only thing is only yn minus 1, yn minus 2, yn minus 3. That means we have y cube, y square term, then dy by dt term, then constant term, then b into y. So like that we have. Yeah, you can see here. Right. So output is taken as the first state variable. The next state variable is derivative of output. Next state variable second derivative of output. Therefore y triple dot is x3 dot. Therefore we can write d cube y by dt cube as x3 dot plus 6x3 plus 11x2 plus 6x1 plus u equal to u in the same style. Therefore x3 dot is this written in the proper form. x1 dot is x2, x2 dot equal to x3. We can write using this or the same as whatever we have discussed in the generalization. So if we see here the vector matrix notation of this state equations, so we can see the last row containing the 6, 11, 6 in the negative sign in the written in the reverse order, minus 6, minus 11, minus 6. So row, the element just above the diagonal elements are 1, 1. Remaining elements are 0. The last element corresponding to B, that is last row, is 1. Same as this. Same as this. This, and this. That only is written here. This, and this. So y is equal to x1. Therefore, y is 1, 0, 0, x1, x2. This is again same as this. Instead of xn, we have x3 because it is a third order differential equation. And we can represent this with the help of a block diagram. After all, we want to express these three state equations and the output equations. Therefore, you have x3 dot, x3, x2, x1, y input. So first we need x3 dot. How to find out x3 dot? Minus 6x1. Therefore, from x1 you should have 6 with again 6. From x2 you should have 11. From x3 you should have 6. Therefore 6x1, 11x2, 6x3 have to be with the minus sign, therefore subtracted. This is input u. So u minus 6x3 minus 11x2 minus 6x1. That is this. That is where x3 dot. So I said x3 dot, x3, x2, x1 only you have to put initially and this. How to find out x3 from this? x3 dot to x3 is just integrator, that's all. So x3. Okay, x3 is x2 dot. From x2 dot, how to put x2? Just put integrator or 1 by s, that's all. x2 is nothing but x1 dot. From x1 dot, how to put x1? Integrator, that's all. So this is again very, very simple. Right. Then one more thing, output. Output is x1. Therefore, this x1 is taken as output. In the next module, next video, I will discuss about the state space representation of the system with zeros using the same phase variable concept. Till I meet you in the next module, thank you. Enjoy watching this video. Share this with the learning community so that it reaches the huge section of the learning community for their benefit. Thank you very much.